is a four-part cycle that repeats itself. And we can refer to this as a cyclical derivative if we want. So let's look at the derivative of sine of x. That becomes cos of x. The derivative of cos of x then becomes minus sine of x. So that's the second derivative of sine. And then if we differentiate minus sine of x, that'll give us minus cos of x, the third derivative of sine. And then when we differentiate minus cos of x, we're back to where we started, back to sine of x. So if we look at some numbers associated with those cycles there, so those numbers in blue are the first time through this cycle that I just walked you through there. Those yellow numbers are the derivative numbers when that cycle starts to repeat itself the second time. And it's hardly surprising that those numbers are spaced by 4 because this is a four-part cycle. So if you have a derivative that's 0, now that really doesn't exist, but just in working with these patterns here, instead of referring to the original function, we'll just call it the 0th derivative. But of course, I really mean it's our starting function, our y equals sine of x. So if you have 0, 4, 8, 12, you will, as a higher order derivative, you will know that that's going to end up being sine of x. If you have a higher order derivative that's 1, 5, 9, etc., that's cos of x. And I think you can figure the rest out, but just quickly, 2, 6, and keep adding 4, of course, to get 10 and 14. All those higher order derivatives will be equal to minus sine of x. And lastly, if you start at 3 and keep adding 4 to get 7, 11, etc., you'll end up with minus cos of x. So let's extend that pattern out kind of linearly so we can kind of see it a little bit better organized and devise a plan to try to predict what a very, very large higher order derivative might be. So if we have a derivative number that's 0, 4, 8, 12, 16, etc., we know that's going to give us sine of x. And if we have 1, 5, 9, 13, 17, etc., that's cos of x. And starting on 2 and going up by 4, we'll end up with higher order derivatives that are all equal to minus sine of x. And starting on 3 and going up in 4, all those higher order derivatives will be equal to minus cos of x. So there's a lot of numbers there, and those are, of course, 4 arithmetic sequences there that we just have to, I guess, dissect and make sure we understand that. I think that for me, when I'm working with this, I just look at the blue numbers and say, if I'm starting on sine of x, I'm just going to keep track of my 0, 1, 2, and 3 derivatives, and then I can add 4 to those as many times as I guess I need to determine what the higher order derivative is actually going to be. And instead of doing that, creating long lists of numbers, there's a far wiser approach. And of course, that's looking at dividing this by 4, any of those derivative numbers in front of you. And since this is a four-part cycle, which is why this works and makes a lot of sense. So if we divide any of those sine of x numbers by 4, the remainder is always 0. So 0 divided by 4, 4 divided by 4, 8 divided by 4, all 0. If we divide any of those cos of x derivative numbers by 4, we can see that all those remainders are 1. And similarly with the minus sine of x, if we divide any of those numbers by 4, we get a remainder 2. And the last one, if we divide any of those numbers by 4, we get a remainder 3. And hopefully you're noticing that the remainder is actually the derivative number that we need. It's that simple. So if you have a higher order derivative that you're interested in determining, instead of actually differentiating it, say like 40 times, just divide 40 by 4. And if the remainder is 0, you know your higher order derivative is going to be sine of x. And if the remainder is 1, you need the first derivative. If the remainder is 2, you need the second derivative of sine of x. I should be clear. And if your remainder is 3, you need the fourth derivative of sine of x. So let's look at that, obviously in an example where we'll differentiate sine of x 43 times, and not physically doing that, try to determine what the 43rd derivative of sine of x would be. So we take the number 43 and we divide it by 4, and we realize it goes in 10 times evenly, but with a remainder of 3, and that's really all that we care about. And remember, we're dividing by 4 because we have determined that this is a four-part cycle. And since that's the remainder of 3, we just need the third derivative of sine of x. And if you're If it's been a while and you're rusty, and even if it's right now and you don't remember what the third derivative of sine of x is, well, it's not going to take you too long to go through those first three derivatives and figure out that the third derivative of sine of x is minus cos of x. Therefore, the 43rd derivative of sine of x has to also be minus cos of x, because 43 and 3 both have the same remainder upon division by 4. And one other thing too, you don't always have to start on y equals sine of x. You can start anywhere in this 4-part cycle. So if you're interested in figuring out a higher order derivative of cos of x, or minus sine of x, or minus cos of x, you use exactly the same approach that I outlined here. And I don't think we need to go through it, but just very quickly, if you're taking maybe the 40th derivative of cos of x, then you're just going to call cos of x your 0, and minus sine of x would be your first derivative, etc. And you're still going to divide, and as long as you know what your first three derivatives are, and you're calling your initial function as 0, you can figure out what your higher order derivative is going to be. And incidentally here as well, in computing science and in mathematics, something called a modulo operation is exactly what we're working with here. Not to be confused with something a little bit more advanced, modular arithmetic, that you encounter in number theory. So if you see an MOD in math, you're tinkering around with the numbers and remainders, and a modulo operation is all it's concerned with is what the remainder actually is. So if it's 0 mod 4, we're just saying, what is the remainder of if we divide 0 by 4? That's kind of a weird one, because 0, of course, is always going to be, it's going to go in, any number will divide in evenly to 0. So let's look at one of the yellow ones here, farther down the list, 7 mod 4. What's the remainder when you divide 7 by 4? And that, of course, is equal to 3. Obviously, you don't need to know that for the purposes of this course, but if you encounter that later in your mathematical travels, try to make that connection as well. Okay, lastly, this is becoming a common wrap-up. Let's use Wolfram Alpha, and we'll just see how easy it is to type this in and confirm our previous result. If you ask Wolfram Alpha for the 43rd derivative of any function, I guess it will do it. You might want to experiment with that, but I'm going to say play safe and just work with our sinusoidals here, which we know are definitely going to be cyclical. So what is the 43rd derivative of sine of x? And remember, we just divided that by 4, realized that a remainder of 3, so we needed the third derivative, and we got minus cos of x, which Wolfram Alpha is supporting that answer, which is great. And if you want the 143rd derivative, it's the same thing. You divide that by 4, figure out what your remainder is, and apparently that remainder is 3 again. Okay, so you can tinker with that. And again, just to illustrate that last part, if we're working with cos of x, and if I ask you what the, let's say, 41st derivative is of cos of x, then you realize, okay, my remainder of when I divide 41 by 4 is 1, so I just really need the first derivative of cos of x. And you'll see that that's minus sine of x. So that pattern can be applied to any of those 4 functions that occur in this 4-part cycle.